in this session we will try to understand what are basically class diagrams. We will try to understand the fundamentals of it. We'll try to see different types of classes like abstract class or interfaces. How can they be represented using class diagrams, and see the same, that how we can implement them in the technical documents. Class diagram basically form one of the very basic entities for technical documents. As I said previously, that some of the diagrams are compulsory and very much needed to describe any technical architecture. Like one of the diagrams which we discussed previously was a use case diagram, which is very you can say a building block to gather requirements. In the same way, class diagrams are basically very useful, to understand the static part of a project. When we look at any technical architecture design, there are two ways of viewing it. One is the dynamic part of the project, and one is the static part of the project, or we can say the static architecture of a project and the dynamic architecture of a project. To give you a better understanding of the static architecture and dynamic architecture, we'll try to map the same with a real example. When any civil engineer basically builds up architecture, he can probably define the static architecture, saying, okay, that this will be the pillars, this will be the beam, this will be probably the rooms, the sizes, the length, and etc. But what happens if suppose people start living inside it, and then people start they start staying inside the building, or they start traveling over the bridge, or whatever kind of design, or whatever design for which it is made for. So in the sense, that is a dynamic part of the project, or we'll say when actually it comes into creation. So we can say one is a static architecture of a project, and one we can say a dynamic architecture of a project. Both of these views are very important when we write a technical document. So class is, I'll just revise these basic definitions. If you have already done object-oriented programming, then you don't need to really look into this. But in case not, we will just revise the basic definitions. So it is basically a prototype which helps us to create objects. So you can say it's like a data type, and by using the data type you can create objects. As I said previously, they define the static part of a project. They define a blueprint, and from that blueprint objects are created. In UML, the UML notation to define a class diagram is basically by defining a simple rectangle, as shown in the above video, and then dividing this rectangle into three parts. The first part is where you define the class name of the class name. Like example, here the class is CLS customer, so I've defined it as CLS customer. So that is a class name for the class what you are trying to define in using class diagram. The second section consists of properties for the classes. So I have two properties here, customer code and customer name, and also I can define the data type. The third one has the method names. So for example, I have add customer here, and the add customer basically returns a boolean value. So class, there are three sections. The topmost section which represents the class name, second section represents the attributes, and third section represents the methods. So whenever you draw the class diagram in your document, or whenever you try to express your class diagram in a design document, this is the UML way of notation, or UML way of defining the class diagram by the three sections. Now that we have understood the fundamentals of how to represent a class diagram in UML by using the three sections, where we defined in the first section the class name, the second section the property, and the third section the method name. But how do we represent these entities, that is the properties, the methods, as public, private, or protected? In order to express these methods, or express their visibility outside the class to the client world, we use some notations. For instance, a plus notation before the property or before the method name indicates that this is a public method, or this is a public property. So if any client creates an object of the CLS customer, he will be able to call the customer code property, or he will be able to set or get the customer code property depending on how the property is exposed, and also he will be able to call the add customer method. The negative sign before the property or the method indicates that this is a private entity, or this is a private property or a private method. So customers or clients, I'll say, not customers, sorry, clients who create objects of CLS customer will not be able to view the net profit property. So it is encapsulated and it is protected from the outside world. The in-between property, that is we can say, or we can say the in-between visibility, is called as a protected visibility. The protected visibility is defined by using the hash symbol. So if you define the property or the method using the hash symbol, it can only be viewed by classes who inherit from these classes. Means, in the sense, if I want to use the discount property, then I need to inherit from CLS customer, then only I will be able to view the discount property, or else I won't be able to view the discount property. So if you want to ensure that you want to make visible your entity and the methods only in the hierarchical, or only in the inheritance hierarchy, or only through the generalization specialization relationship, at those moments only you will use the protected property. So the plus indicates the public property, the minus indicates that it's a private property or private method, depending on where you show the notation in the class diagram, and the hash indicates a protected property. That means only the inherited classes, or the child classes who inherit from this class can access the protected property. Now, one of the important thing is that a single class cannot represent the whole module in a project. So for example, we have defined a customer class. Definitely the customer class has to interact with other classes to fulfill the functionality. So it's possible that for example, in the video I have shown order class which interacts with the payment class to achieve the full functionality, is saying that the order, once you place the order, it will use the payment class to do the payment. So a class itself cannot represent a system. It's basically the interaction between these classes represents the system. So definitely when you design your technical document, and you write your technical document, you'll definitely need to show interaction between the classes, and this interaction in UML is shown by using the arrow key as shown in the figure, or as shown in the video. You can define this arrow key as a left to right, top to bottom, right to left, depending on your situation. So basically a simple arrow key, and then defining, saying that what is defining a simple one letter word or action saying what is going to happen. For example, I am saying here the order class is going to use the payment class, and he's going to pay the order using the payment class. Okay, now that we have understood that yes, that a class cannot represent a whole system, but basically it is the interaction between these classes can represent a system, it's time to understand how these relationships are further classified. Means what? Here's a simple relationship which I am showing. I'm showing that I have a customer class, and the customer class can have an address class to show the addresses. Now in reality it's very much possible, or in real life it's very much possible that that one customer can have many addresses. I mean to say, it probably we can say that the customer has a branch office, so he has one address. He has a head office, so he has some other address. So in sense a customer can have multiple addresses. That means that a single customer object will have many address objects, and this is termed as multiplicity. Means now we are going one level above the relationships, or we are going into more detail of the relationship, saying okay, you both guys interact together, but with what kind of multiplicity you are interacting. That's shown by using a simple stick, which I can show, which you can see in your video. And second, we show it by using the star and the number, that how much is the multiplicity. For instance, over here I am saying okay, from respect to customer I need at least one object, and it's very much possible that I can have many objects. So in this sense, what it means to say is that the customer object should have at least one address, and also I mean to say, if he has many addresses, then he can have many objects. So one signifies saying the must, and the many signifies saying that the upper limit of or we can say the upper limit of the instances. So in this way we define the multiplicity between two classes. The other important relationship between classes are aggregation and composition. Means what? You can see in a figure that I have shown a bread, and then the bread can be further broken into slices, and we can apply a butter on the bread. Now the bread represents, you can say, the main object, and that main object consists of a lot of slices. Means what? The bread doesn't exist without the slices. In short, if your class is creating an object of other class and lifetime of the object or the lifetime of both of these objects are same, then it is termed as composition, and that is represented by using a dark diamond. The life of slices is equal to the life of the bread, in the sense if you eat all the slices, then definitely you have eaten all the bread, or if you have eaten all the bread, then that means that you have eaten all the slices. So in the sense, the relationship between the bread and slices is more of composition. So the bread is composed of slices. So if you have classes which create object of other classes, and the lifetime of both the aggregated object as well as the parent object are same, that means that it is a composition relationship. In the aggregation relationship, it is just opposite to what is composition, in the sense the lifetime of both of the objects or the aggregated objects are not same. So for instance, I can eat the butter irrespective of the slices, in the sense the slices uses the butter object, but the butter can exist as a independent entity and the slice can exist as an independent entity. In other sentence, what we are trying to say is that the lifetime of the butter and the lifetime of the bread is not same. So if you have a class who creates an object of other class, and you can use both of these objects independently, or the lifetime of both of these objects are not dependent on each other, then it's an aggregation relationship, and that is defined by an empty diamond. So this is the second type of relationship which we have defined. The previous one we have defined is the multiplicity relationship, or the type of relationship, and this one we have defined is the aggregation and the composition relationship. So we can just revise the definition. In aggregation, the whole object can exist without the aggregated object. So the butter can exist without the slices. In composition, the whole object cannot exist without the aggregated objects. Like the slices cannot exist without the bread, and the bread cannot exist without the slices. If you eat the bread, you have eaten the slices. If you have eaten the slices, you have eaten the bread. In this section, we will try to understand basically composite structures. Basically, composite structure are nothing but UML notations which are used to simplify the multiplicity complications in complicated class diagrams. For example, at the left hand side you can see that it's a normal diagram which I've shown. So there is one customer can have many address, and every address can have multiple phones. Now this diagram looks very complicated. I mean to say, if you have like 5 or 6 hierarchies like this, I'm sure that it can fill up your whole technical document. So what you do is that you take this customer class and show it as a whole relationship. So here's a customer class now as a complete box, and saying that okay, this customer class has a lot of address and then it has a lot of phones. So in this way you have minimized, or we can say you have made the diagram more simple. So it is just the way of showing diagram in a more simple form, or you can say the way of showing complicated multiplicity relationships in a simple form. The type of association between classes are reflexive associations. In reflexive associations, basically it shows that how two instances of the same classes are associated with each other. Now let's try to understand this with an example. For instance, you can see that we have a customer class, and one customer class can have many address classes. Now what happens is, within the address class itself, now when we say many address classes, mean this is basically a collection. Now Within this collection, one of the address objects can be a head office object, and for every head office object you can have many regional address objects. So in this sense, again within this collection you have association which specifies the multiplicity between the instances of similar objects, or between the instances of the same class. So this is denoted by using a joint rectangle, as you can see here, and showing the multiplicity sign. So what I'm showing here is that there can be either 0 instances of a head office object, or there can be 1 instance of a head office object, and these instances and 1 instance of a head office object can have many instances or 0 instances of a regional address object. So if you want to show the association between the same collection of object itself, at that time you will need reflexive associations. Business entity and service classes. This section which I'm showing it now on the video is not basically related to UML as such, but we need to understand some vocabularies like business entity, service classes, because when you design or when you write your technical document, probably these classes, these terminologies are used, and these terminologies are constant across the IT industry. Business entity classes are nothing but, or business entity objects are nothing but, they represent persistent information like tables of a database. For example, I have over here I have a customer table. So basically the customer table can have a customer code, a customer address, customer phone number, and this table will have a class called a CLS customer, which will represent exactly the same information what is there in the database. So this is called as a business entity class. Means it represents a table, or it represents a logical unit of entity information from the database. Now on this business entity class, you will definitely need to define a behavior. For example, one of the behavior you like to define is add, next, previous, get item. So the service defines a behavior on the entity class. So it's like separating the data from the behavior. So your data resides in the business entity class, while the behavior is your service class. Whenever you design your technical architecture, and on those moments, means when you write your technical architecture document, you would like to represent these kind of scenarios where you would want to separate the entity, or we can say the data, from the behavior, in order to make the system more flexible. Now what happens is, the terminologies used to define or to put down on the technical document sometimes can be very custom. It's very much possible that I can write this business entity class as something called as probably a custom class, or I can say that it's something I can name it as a data class. Now a data class vocabulary is not consistent across the IT industry. Means you have to make someone explain that what does a data class mean. So rather than using custom terminologies, you can use these IT defined, or what you call as the IT industry standard terminologies like the business entity class, the service class. So whenever you define your behavior, you define it with the name of the service. Means you can say probably CLS service customer. So that says me that this has a behavior. CLS customer is a business entity class. In the same way, there are situations where you would like to represent persistent information related to system. For example, I would like to represent persistent information related to system registry. So at that time you need to define a system entity class. And if you want to define a behavior for the system entity class, then use the system service class. The difference between system and business is that business classes represent user point of view of information. For example, if you look at the previous slide, you can see that customer is a user defined vocabulary, or it's something which is related to user's perspective, while audit is something which is related to more of a technical perspective. So any kind of technical encapsulations or any kind of technical understanding or any kind of technical classes are represented by using system entity and system service classes. So if you want to represent a system behavior, you can use the system service class. If you want to represent a system information, you can use the system entity class. Because the vocabulary system registry will not be understood by the end user, but yes, the vocabulary customer will be understood by the end user. So it's basically the choice between business and system is mainly on the basis of technical and what you call as a business vocabulary. The other important part, or the other important relationship which needs to be depicted, or which needs to be shown in any class diagram, is the parent-child relationship, or we can say the inheritance relationship. And in other words, I can say a generalization specialization relationship. So basically in UML, you can show the parent-child relationship using the arrow key. When we say arrow key, basically over here in the diagram, the arrow key is a bit dark, but that's not a way. Okay, so it's basically more of like this, with a empty arrow, or I can say a hollow type of arrow, and then showing the relationship. So with this symbol, you say that the CLS mobile is a child of CLS phone. The CLS landline is a child of CLS phone. So CLS phone is the parent, while CLS landline and CLS mobiles are the child classes. So what happens basically over here means what? First, let's try to understand this generalization specialization relationship. Basically, CLS phone is a generalized thinking, or a general or abstract thinking of a phone, but CLS landline and CLS mobile become concrete, so they become specialized thinking. So if you want to define such kind of relationship, or if you want to show such kind of relationship in your technical document, or you basically use the arrow key, the hollow arrow key, and you show the parent class relationship by showing the parent at the top, the hollow arrow key, and then the specialized classes. So over here you can see that the parent class has a phone number, but while the landline child class has a wired connection, because that's extra property. So the CLS landline class will get the phone number property as well as add phone details, but he will himself add extra one more property saying wired connection, because it is more specialized, more specialized and related to him. In the same way, the CLS mobile will get the phone number and the add phone details entities, but he will add an extra SIM card connection property to it himself, because that is his specialized, or we can say that is his specialized representation of a mobile. This is form a very important part of a technical design document, or of a software project, because interfaces represent the communication vocabulary between two classes. In UML, we represent interface by a simple class notation, because at the base, interface is nothing but again a class. So basically you have a simple rectangle, you have the three sections which we had described first while we had talked about the class diagram, the class UML notations. You then give an interface name. For example, here it is iContext, so that is your class name, or we can say that is currently the interface name. The only difference which is there while representing an interface is the type keyword. So you need to say basically type with the left arrow key and the right arrow key, or I'll say the greater than sign and the left and the less than sign at both sides of the type keyword. If you want to show that the interface is been consumed by a client, so basically that's shown by using a circle and then the strongly typed class, or the class which has implemented the interface. For example, here the iContext interface has been implemented by CLS transactions. So the client the client uses the iContext, which internally basically calls the concrete class CLS transactions, or the implemented class, and the consumption by the client to the interface is shown by dotted lines, and at the other end, the iContext, we show a dark line which represents a connection between the implemented class and the interface. So basically interfaces are represented by using the type symbol, the type keyword symbol, and with the left hand and the right hand the greater than and the less than sign at both left and the right sides of the type keyword. The second important class which every language has is abstract class, and abstract class basically are again one of the important parts of any software project. So basically abstract class are represented by using the curly brackets at both left and right hand side and writing the abstract keyword in the class name. So basically we write abstract and then we say the left hand curly brackets and the right hand curly brackets and the class name. So basically I am saying over here this is CLS login, and it's not a simple class, but it's basically a abstract class, and abstract class with a login method. So basically if you want to represent an interface, you use a type, add type when you type where you write the class name. And if you want to use the abstract class, if you want to define abstract class, you basically show two curly brackets at the left and right hand side and write in between abstract. So that is the only difference, when we compare it with common classes. I hope that we were able to make you understand the class UML notations. Now the best way to practice these notations, or best way to implement these notations in your software project, is basically whenever you discuss with your friends about software architecture, or whenever you explain anyone the software architecture, always try to use these notations as much as possible. Don't try to write generic things. For example, if you are showing abstract class, don't show a box and say okay, this is abstract class. Show a curly bracket. If you are showing inheritance hierarchy, don't say this is inherits. Show a class, show the hollow arrow key, and then show the child class. So the whole point over here is that basically even when you're talking or discussing with anyone, or writing down on a paper, or showing on a board, always try to use the UML notations, and that's the best way to practice, because later on when you actually make a technical design document, it's just about using the tools and putting the things properly. So we hope that you enjoyed this session of the class diagrams, and see you in the next sessions of other UML diagrams.